Hello, chemistry students. This video is discussing the trends we see in removing more than one electron, or you can think of it in terms of successive ionization energies. So let's define ionization energy. That is the amount of energy basically to remove an electron. If you want a more specific definition, ionization energy is the amount of energy required to remove an electron from an atom or an ion in its gaseous state, okay? So basically, if you remove an electron, you're forming an ion, a cation, right? Removing negativity leaves you with a positive charge. So this video is focusing on, well, what are the trends we see when we remove more than one electron? So the removal of each successive electron requires more energy. So to remove two electrons requires more than energy than to remove one. Why is that? Well, you can think of it as the overall species that you're removing electrons begins to contract because the number of protons are going to start outnumbering the electrons and they're going to have a greater pull. So what happens is there's going to be an overall shrinkage in size, and now the electrons that remain are closer to the nucleus, and according to Coulomb's law, it's harder to pull them apart. So now that the outer electrons are closer, it's going to be harder to remove. Just think of magnets, right? As they are closer, they're harder to remove. So there's a regular increase in energy for each valence electron. So, it requires more energy to remove two electrons than it does one. It requires more energy to remove three. That just makes sense because, again, the proton is going to start out, the protons are going to start outnumbering the electrons more and more. But what the purpose of this video is, there is a huge increase when core electrons are removed. Now, a lot of people struggle with this and they don't really get that. So I wanted to focus on this primarily. So here we have a table from your basic chem book. And on the y-axis, it shows kilojoules per mole. So the amount of kilojoules of energy per mole of electrons removed from these elements. And they have sodium and magnesium to compare. The first thing is first ionization energy. What that basically means, and it's written, a lot of times you'll see it as IE1. The amount of energy to remove that electron, you see, okay, from left to right. So if we had a periodic table, right? You have a periodic table. Here's a periodic table. As you go from left to right, ionization energy increases. Well, why? As I go from left to right, the electrons are in the same principal quantum number or energy level, but my Z effective charge goes up. So the number of protons increases and my Z effective charge. So it increases, right? It goes up as I go left to right. Now, it makes sense that ionization energy decreases. So it actually decreases as I go down a group because the valence shell is further away from the nucleus, or it's easier to remove. So now let's look at sodium and magnesium. Sodium's group 1, magnesium's group 2. We have an ionization energy, and as we go left to right, we see magnesium, because it has a greater effective nuclear charge. It has 12 total protons. We can say 12 electrons, and then this has 11 protons and 11 electrons. So as a result, it's going to have a greater effective nuclear charge. Its first ionization energy is a lot greater. When we go to the second ionization energy, there's a big jump in sodium. So why is that? Well, if you think of sodium, right? Sodium, basically, if I want to make this a simple Bohr model, we have 2 electrons in the first energy level, 8 electrons in the second, and then that 11th electron, that's why it's in group 1, it's in your third energy level, principal quantum number 3. It's in the S block. It's in the first position, so it's a 3s1, okay? Also, you'll see later with Lewis dot symbols, they just draw 1 dot. So if I remove that 1 electron, okay, it requires energy, but once I remove that, right, Now I have a positive charge, and I no longer have 11 electrons or 3s1. Now where am I going? I now have 10 electrons, and I'm actually in my second energy level. And the whole purpose of sodium wanting to lose an electron is to have that configuration of a 1s2, 2s2, 2p6 noble gas like neon. So what happens is to remove that one of those 2p6 electrons, there's a huge jump in energy. Now, when you compare that to magnesium, magnesium's in a different situation. Magnesium, right? It's got 12 electrons, 2, 8, 2. So when you remove the first one, and you do have a magnesium 2 plus, 2, 8, there's still 11 electrons. There's one electron in that outermost shell. So when you remove one, there's still one left. So to remove the second, it requires more energy than the first, but compared to sodium second ionization energy, it's actually smaller. Where do we see a huge increase? Well, now when we go to the third, now with sodium, to remove the third ionization energy, okay? For sodium, this is actually going to be not the 2s 2p6, this would be a 2p5. So you're already in that core shell of the second energy level. So it goes up, but what we see is for the third ionization energy of magnesium, it skyrockets. And why is that? Well, now you're no longer removing, what's in the valence shell. So this was a 3s2 when we removed the first ionization energy. When you go to the second ionization energy, it's a 3s1. Now you would be removing a 2p6. So it skyrockets. Well, how come to remove a 2p6 requires more energy than a 2p5? Well, that goes back to our general trend. Left to right, ionization energies increases because of Z effective, your effective nuclear charge, and there's more protons, so it's harder to remove 3. But there's that kind of confusing part for students. So what's the best way of thinking of it? This table does a great job. This table just, everything in pink right here is when you have a noble gas configuration of neon. So neon, right? Its noble electron configuration would be 1s2, 2s2, 2p6. So once you have that second energy level filled, it's happy. Well, we just said sodium's a 3s1, right? Or you can just think of it as one valence electron. So once you lose that one, now where are you? You're like neon. You don't want to lose anymore, right? Now, if we look at the basic trend of ionization energy, right? This is kind of confusing because this is period 2. So this is actually going left. It looks like I'm going down a group, but I'm not. I'm actually going across, I'm sorry, the third energy level. I'm going across the third period here, and I see, it looks like I'm going down a group, but it's third period. Now, if I go to magnesium, you can think of a magnesium. It's got 2 valence electrons, or a 3s2. So this would make it a 3s1, like I said, if I remove this. But, once I remove this one, now the 3s is gone. And I'm happy because I have a 2p6 configuration like neon. But to remove a third electron, right? Because now, if these two are gone, I'm in that core electron, that noble gas configuration, it skyrockets. So aluminum, it's group 3a. It has 3 valence electrons. So the first one requires energy. The second one requires more energy. The third requires more, but where do I see a huge jump? The fourth. Why do I see a fourth with a huge jump? Because now you're getting into that 2p6 electron, right? Because this is a 3s2, 3p1. And we can even see that with aluminum, there's a little inconsistency here, right? To remove that 3p1, It's actually easier than the 3s2 to remove that electron for the magnesium. So if we go to silicon, it's in group 4. So if you remove 1, 2, 3, 4, each one increases, but to remove the 5th, it skyrockets. Why? Because now you're removing what would be considered a neon electron configuration. So I hope this video makes sense with understanding successive ionization energies and why you see these big jumps at certain places. It's basically once you've stripped it of the valence electrons. Once you've removed all those valence electrons and you get into that core, it skyrockets, and that's what this is showing. So thanks for watching. If you guys have any questions, let me know. And